The derivation of the stiffness matrix of any kind of an element by means of the total minimum total potential energy formulation always starts with the strain energy of the system, where you have the strain energy of the element to be given by a volume integral of E epsilon square by 2 dV for solid mechanics, as we've already studied. Now, when I start simplifying this and writing it down in the matrix format that is more suitable to finite element formulation, and also in the sense of material behavior, when we have, if we are going to consider special case or special condition of plane stress, as we have done for the triangular element for making it simpler in terms of formulation, then I can just assume the material matrix to be a matrix D. So instead of E, I replace that with matrix D, and the rest is basically strains, which I can define in a matrix formulation as half of in volume integral of transpose of the strain times the material property D times the strain over dV. Now, since we are considering plane elements which are very thin, that means we also have dV can be written as the thickness of the element Te times the integral times the differential area. So we can also write this as half of area integral T E for the element epsilon transpose d epsilon dA. Now we keep this in mind, and here what we notice very clearly is that all the D is defined as the material definition. That means we already know something about it because we will be given, hopefully for the problem, an E and a V nu. So we will be able to find out what the matrix is for the material properties, and then as a geometric condition we will also know what is the size of the element. So basically the thickness of the element will also be known to us. So the only unknown that I can figure out here is the strain that needs to be provided in this particular formulation. Now, for a condition of in-plane or plane conditions that we've already seen before for thin plate theory, which is only loaded in plane, then we can write our strain vector to be dou u dou x, dou v dou y, dou u dou y plus dou v dou x. So that's the reduced strain for a two-dimensional system which is only acting in the in-plane direction. Now, we know that the strain in this two-dimensional system has these three components: the normal strain and the shear strain. And we also know that this strain is therefore a derivative of the displacement. The displacements are in general composed of the nodal displacements in combination with the shape functions, and the shape functions have already been described in the natural coordinates, right? So if I have to break it down for you, I have the strain, which basically depends on the displacements u and v. The displacements u and v are described by means of shape function times the displacement. The shape functions is a function of r and s, which are in the natural coordinates, because we already did that for description of the element in the previous section. And the displacement behavior is basically just the unknown degrees of freedom in the system. So that is nothing new. So when we try to find out the strain, if we come back to the strain now, the strain is a derivative of x, y of these displacements. And however, the shape functions, which actually need to be partially differentiated, are given in r and s, and that is absolutely impossible to do. So we must carry out a transformation. So a transformation is absolutely necessary from the standard xy to rs, or the other way around, to be able to carry out this partial differentiation. And this transformation of the coordinate is done by means of deriving a Jacobian function, which helps us to find a relation between the natural coordinates and the standard coordinates. It may seem a little bit confusing, but you have to understand that the strain is provided in displacement is going to be a derivative of x and y. However, the displacement themselves are in the form of are dependent on the natural coordinates r and s. So r and s must therefore be related to x and y so as to be able to carry out a partial differentiation on these displacements. So I'm going to now start deriving the Jacobian, which is called the transformation between these two coordinates. So let's take this as a task now. So I'm going to call this the Jacobian. It's not I who coined the term, it's just a standard term which is used for this transformation matrix. To start with, let's just define a random function. Okay, we say a random function f which is dependent on x and y. So if we must find out its derivative, so we want to find out the derivative of f with respect to r and with respect to s, while the variables x and y are actually dependent on r and s. So we can find the derivative as a product of the derivative of the function with respect to x and the derivative of x with respect to r. So it sounds a little bit confusing, but I'm going to write it down in a mathematical format and it will immediately become clear, or maybe you will get reminded of something that you've done in the past. It's basic use of the chain rule. So if I want to find out the partial derivative of f, which is a function of x and y with respect to dr or dou r, then I can write this as a partial derivative of f x y with respect to x times dou x dou r plus partial derivative of x y dou y times dou y dou r. And in the same way, I can write partial derivative of f with respect to s to be equal to partial derivative of f with respect to x dou s plus partial derivative of f dou y dou s. So this is the simple rule of the chain, simple use of the chain rule. And now if I want to write this in a shorter format or in the matrix and vector format, I can write partial derivative of fxy dou r and partial derivative of fxy dou s will be given as dou x dou r dou y dou r dou x dou s dou y dou s. This times, you see that there are common terms here, dou of fxy, dou x, and dou of fxy, dou y. So this particular matrix is now called the Jacobian and can be written as matrix J. The relation therefore can also be inverted. That means we can also write dou f of xy, dou x, dou f of xy, dou y is equal to the Jacobian inverse times dou f of xy, dou r, dou f of xy, dou s. The Jacobian here, J, can also be written as J11, J12, J21, J22, just to keep it simple so you don't have to write those partial derivatives out again and again. So if you want to find out the inverse of this Jacobian, J inverse, then it, of course, you know how to calculate this. So you have to write it as 1 by the determinant of J. So that's J11 times J22 minus J12 times J21 into the transpose of the Jacobian with minus sign. So you know how to do this, or you can also use the tools that you have now in terms of Python or MATLAB to carry out this inversion, and that can be written as 1 of determinant of J times the matrix that I already put out in front of you. So it's relatively simple. However, you still need to understand that this transformation needed to be made. So the Jacobian can therefore be evaluated for any given quadrilateral element by substituting the definition of x and y from the equation that we had proposed using the shape functions into the Jacobian matrix, which is J. And as you can see very clearly from the previous slide here, that is just a derivative of x and y with respect to r and s. And x and y are written in terms of the shape functions, which are therefore written in terms of r and s in the natural coordinate. So that's quite easy to calculate. Okay, now we will keep this part a little bit for later, and we will go on further by going back to this stiffness matrix derivation that we stopped at here. So I'm going to call this equation capital A, and now I want to get back to the equation capital A, where I can now start substituting the strain value.